Hello everyone. Today we're looking at Ethernaut Level 13, which is Gatekeeper One. Now this is a very interesting level, and the goal is to make it past the gatekeeper and register as an entrant to pass this level. So, we take a look at the contract. There's an address for the entrant, and there's a bunch of modifiers, so gate 1, gate 2, and gate 3. And then there's a single function called enter, which takes in a bytes 8 argument called gate key, applies all the three modifiers to it, gate 1, gate 2, and gate 3, and returns a boolean. So assuming we pass all the modifiers, which are just a bunch of require statements, if we pass all the modifiers, it sets the entrant address equal to transaction.origin and returns true, which is what we need to do. So let's get a new instance of the contract and play around with this. So we have our instance. Let's take a look at the three gates that we need to pass. Looking at gate number 1, the require statement here is that message.sender is not equal to the transaction.origin. So this means we have to call this from a smart contract instead of just calling the enter function ourselves. So let's go ahead on Remix and create a new file called gatekeeper1.sol, right? And we'll set it up. Actually, let me just copy paste this code in there so it's easier to keep track of it. So I'll take this, I'll put all this code in here, and we'll create a new contract called attack, which has a reference to the gatekeeper contract. We'll create a reference to the gatekeeper contract, and we'll set it in the constructor. So we'll take a target address and set gatekeeper equals gatekeeper1 at target. Okay, and then we'll create a function called attack, this is external, and we will call this. So we need to pass these three gates, right? Gate 1 is automatically passed because message.sender equals the attack contract, but transaction.origin equals the player address, so my address. So we've already done gate 1. Then we have gate 2, which requires that the gas left up until this point is a multiple of 8,191. We'll come back to this, all right? We'll come back to this and I'll explain to you why. And then we have gate number 3, which has 3 require statements. And what it does is it takes in the gate key, the same gate key we pass over here, it gets forwarded on to gate number 3. It takes in the gate key and it does a bunch of typecasting. It does a bunch of type conversions and wants things to be a certain way. So let's start by breaking this down because this requires a lot of sort of tricky logic to get right. And then we'll come back to gate 2 and I'll explain why. So with gate number 3, the first thing to note is what is the input, right? The input is an 8-byte string or like 8 bytes, right? So 8 bytes, let's represent it in hexadecimal, which means it is 16 hex characters. So the string will look something like this. So 0x, B1, B2, B3, B4, B3, B4, B5, B6, B7, and B8, where each of these represents a hexadecimal character, right? So 2 characters is 1 byte. We need to pass it 8 bytes. So the input is going to look something like this. Now, let's take a look at all of the different requirements. So requirement number 1 is that uint32 typecast from uint64 from the gate key is equal to uint16 of uint64 of the gate key. What does this mean? So let's first look at what uint64 gate key would mean. When we're talking about 8 bytes, right? 8 bytes and 1 byte is equal to 8 bits in binary. uint64 is an unsigned integer type with 64 bits, which means 8 bytes. So when we do uint64 of gate key, what we're essentially doing is converting this value, converting these 8 bytes into the numerical representation. We're not losing any data. We're not creating any new data. We're just converting it from a byte string into a number. All right. So on both sides, uint64 of gate key on the left-hand side and the right-hand side, this is just equivalent to the numerical representation of gate key. All right. So we get some sort of number with 64 bits as the numerical representation of gate key. Where it gets interesting is with the different type conversions now. So on the left-hand side, we have uint32 of uint64 of gate key. What does this imply, right? What does this imply? So once we have the numeric representation, we convert it into a lower type format. So we go from 64 bits of data to 32 bits of data. So we're deleting some information as part of the typecast because a uint32 cannot store the same amount of numbers that a uint64 can. It's a smaller data type. So we're deleting some data in the process of doing so. If we continue to think of this as this byte string, when we convert the 64-bit number into a 32-bit number, what's going to happen is half of this data is lost, and more specifically, the first half of this data is lost. So we lose the first 4 bytes because we're getting rid of the first 4 bytes. 32 bits is only 4 bytes. So now the uint32 version of this is only equivalent to the byte string of B5, B6, B7, and B8. On the right-hand side, we have something similar, except we converted to a uint16, which is an even smaller data type. And in this case, we only are left with the last 2 bytes of the input. So we're only left with B7 and B8. So to fulfill the first condition, to fulfill this condition, one thing off the top, straight up that we know of, is B5 and B6 must be 0. Because for these two to be equal, for this to equal this, it means the B5 and B6 must be zeros, right? Because these two are then functionally the same. So now we have the first requirement cleared. So to clear requirement 1, B5 and B6 must be zeros. Okay, that is requirement number 1. Now let's head on to requirement number 2 in gate number 3. Requirement number 2 is this thing. And it says the uint32 of uint64 of gate key is not equal to the uint64 of gate key. All right? So as we saw earlier, the uint32 uint64 of gate key is equivalent to B5, B6, B7, B8, and the uint64 of gate key is equivalent to the full string, right? It's all the bytes, no data loss over there. So for them to not be equal, it means that B1, B2, B3, and B4 must not all be zeros, right? So because this is functionally equivalent to saying that this string is not equal to this byte string. And for this to be true, if we pad it with zeros, so we want this is not equal to this, which means B1, B2, B3, B4 is not equal to zeros. All right, so we can have some data over there. As long as all 4 of them are not zeros, we pass requirement number 2. Now looking at requirement number 3, requirement number 3 is slightly more tricky. And what it says that uint32 of uint64 of gate key is equivalent to uint16 of uint160 of transaction.origin. All right, so for the left-hand side, we know that this is equal, the left-hand side is equal to B5, B6, B7, B8. For the right-hand side, what's happening is uint160 is equal to 20 bytes, right? Which is also equal to the length of an address on Ethereum. Length of an address on Ethereum. The ETH addresses are 40 hex characters, which is 20 bytes. So uint160 converts an address to its numerical representation, right? So uint160 transaction.origin is equal to the numerical representation of the address. And then when we do uint16, change uint160 to transaction.origin, we are left with only the last 2 bytes, the last 16 bits of this number. So we are left with last 2 bytes of transaction.origin. And the goal now is to say that 0x B5, B6, B7, B8 is equal to the last 2 bytes of transaction.origin. Now, from requirement number 1, we have seen B5 and B6 must be zeros. So, this is the B5 and B6 values are zeros. So essentially what we're looking for is B7 and B8 to be equal to the last 2 bytes of transaction.origin. All right. So we have all of our requirements for gate number 3 now. Let me just list all of them here together. So requirement 1 is B5 and B6 must be zeros. Requirement number 2 is B1, B2, B3, B4 must not all be zeros. And requirement number 3 is B7, B8 is equal to last 2 bytes of transaction.origin. Okay? This is to clear gate number 3. I'm going to delete all these comments for gate number 3. So we'll only keep the final requirements that we have figured out. So at this point, we should be able to clear gate number 3, assuming we follow these requirements, and we should be able to clear gate number 1. Now let's talk about gate number 2. Gate number 2, what it does is it gets the amount of gas left up until this point and requires that it is a multiple of 8191, right? So the modulus of gas left with 8191 must be 0. This is something that we cannot hard code. So the way it works is when we compile Solidity, right? When we compile Solidity, it turns into bytecode, which goes into like low-level opcodes. So every operation we do, if we're doing like 1 plus 2 in Solidity, this goes into bytecode as like an add opcode, and then there's like a multiply opcode, a divide opcode, and so on and so forth, right? There's a bunch of opcodes. Each opcode costs a certain amount of gas, right? And gas left is a global Solidity function that returns amount of gas left at this point. So, when we initially call this attack function on our contract, we'll give it some amount of gas. Then the attack function will go ahead and call the enter function over here, which will take some amount of gas, which will call, the Gatekeeper One the Gate 1 modifier, which will take some amount of gas. Then we'll go to Gate 2 modifier, and gas left will return how much gas is left at that point from when we started. Now, we cannot really hard code this because depending on what Solidity version you're using, what compiler version you're using, what optimizations you've applied, this can change a little bit because when Solidity goes into bytecode, different Solidity versions over time have had more and more optimizations come in that try to overall reduce the amount of gas that is used. So even if I was to hard code it, it would work for my setting, right? It would work for my compiler version, my optimizer settings, my values, and things like that. You could go ahead and investigate this code in opcodes, calculate a precise gas value. This is a bit of a pain in the ass to do, right? We are not going to do that. Instead, what we can do is we can think of the total amount of gas this function will need in terms of an equation, right? So we know at gate number 2, the amount of gas that must be left needs to be a multiple of 8191, right? So total gas equals 8191 times some multiple, let's say k, plus some value I, right? And this can be anything. This is just, this is the amount of gas that we must have left at this point. So at this point, we must have some multiple of 8191 gas left. And then up until this point, before we get here, we have spent some amount of gas I, right? We can hard code k. We can hard code k, let's say k equals 3. This can be whatever, I'm just using 3 as an example. So total gas that needs to be supplied to the function is 8191 times 3 plus some value I. And we need to figure out what I is. And instead of trying to calculate a precise value of I, what we can do is we can brute force the value of I. All right? And that will make it much easier. With all of this in mind, let's start writing the code for this function. All right, so gate number 1, we don't need to write any special code for it. We automatically pass that level. Gate number 3, we do need to write code for this. And ideally, we need to write some efficient code for this, so we're not modifying individual bits in a byte string ourselves. And here we introduce the concept of bit masking. Bit masking implies using bitwise operators, such as AND, to perform binary operations on data. And essentially what it means is, in binary, the AND operator, the bitwise AND operator, what it does is if you have 1 and 0, this equals 0. If you have 0 and 0, this equals 0. And if you have 1 and 1, this equals 1. Right? It is the AND operator on 2 bits of information. So what we're going to do is we're going to declare the byte state gate key, and we'll keep all of these requirements in mind. Take the numerical representation of transaction.origin, and we apply a bitwise operator to it, the AND operator. And now the way to think of this value is 64 bits, right? It is ones and zeros that add up to a length of 64 characters. And the requirements here are that we need to keep some values, B5 and B6 specifically must be 0, B1, B2, B3, B4 must not all be zeros, and B7 and B8 must be equal to the last 2 bytes of transaction.origin. We can simplify requirement number 2 a little bit. Instead of saying they must not all be zeros, what we can just do is say B1, B2, B3, B4 is equal to the first 4 bytes of transaction.origin, because they're not all zeros either, right? It can be any value that's not all zeros, so they might as well be equal to the first 4 bytes of transaction.origin. And then we end up with this simplified version where the first 4 bytes and the last 2 bytes are equal to transaction.origin, and B5 and B6 are zeros. So if we represent 64 bits in hexadecimal, again, this is equivalent to 2 hexadecimal characters is 1 byte, 64 bits is 8 bytes, so it's 16 characters in hexadecimal, and let's go through it. So we want the first 4 bytes to be equal to tx.origin, which is whatever values, so we'll set it to be FF, 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 FF. These are 4 bytes, and F in hexadecimal is equal to 1, 1 in binary. So FF, 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 FF is equal to 1, 1, 1, 1, 1, 1, 1, 1, and then this, these 16 bits essentially. So what we're doing is we're telling it, okay, the gate key is the numeric, the 64 bits of transaction.origin, and then from those 64 bits, the first 16 bits are equal to whatever is in there, right? So if the first 16 bits, it's like 1 and 1 will equal 1, or if it's 0, then 0 and 1 will equal 0. So B1, B2, B3, and B4 get set to the first 4 bytes of transaction.origin. Then B5 and B6 must be zeros. So we set it to be 0, 0, 0, 0. So regardless of what the value is here, we force these 2 bytes to be zeros, right? And then again at the end, we want the last 2 bytes to equal tx.origin. So again, we set it to FF, FF. This whole thing overall satisfies the 3 requirements. Now we just need to convert it to a byte safe string. So we take this raw binary data, convert it to a byte safe string, and that is gate number 3 done. So gate 1 and gate 3 are done. Now for gate number 2, we need to brute force the value of I. So we'll do for uint 256 I equals 0, and I is less than some value. It can be whatever. Let's say we brute force from, say, 0 to 300. And for each of these I values, we'll calculate total gas equals I plus 8191 times 3, right? And then what we're going to do is we're going to call gatekeeper.enter with the gas value of total gas, and we give it the gate key as an argument, right? So we run this in brute force, and if it passes, it passes. If it doesn't pass, it doesn't pass. Well, actually, this is going to cause a revert if we do it this way. So instead, we need to do a lower level call. We can get rid of these things over here. Actually, we don't need this. We're going to need to do a lower level call, and we'll take the address of the target contract here. And what we're going to do is we're going to get a result value back, and we'll do a low level dot call. So we'll do underscore target dot call with a gas value of total gas, and we'll call it with some data that is equivalent to abi.encode with signature, and this is the enter function, which takes in a bytes 8 value, and the actual value is gate key, right? And then what we're going to do is if result break, right? And we try to compile this, and oops, we're getting an error. Explicit type conversion not allowed from address to uint64. Yes, so we cannot convert an address directly to uint64. We need to first add an intermediary uint160. That shouldn't affect anything. And now at this point, we are ready to go. So we have this contract ready. We head over to deploy and make sure you're in the injected provider, select the right contract, click deploy, and we'll wait for this to go through. And now that it has been deployed, head back to Ethernaut, take your instance address and copy the instance address, provide it as the target, and call attack. This should open up MetaMask. Click confirm, and we'll wait for this transaction to go through as well. All right, now that the attack transaction has completed, let's head back to Ethernaut and let's check what the entrant address is. So if we just do await contract.entrant, you will see this is equal to my player address now. So we should be good to go. Click submit instance and wait for this to go through. And amazing, we have passed this level. We'll try our hand with the second Gatekeeper level. So hopefully you learned something. This was a very enjoyable level for me to record. Hopefully you learned something new, and I'll see you in the next one, which is Gatekeeper 2, even more interesting. So cheers, I'll see you.